Unit 1, video lecture number 14 on derivatives of logarithmic functions. So we're going to investigate what is the derivative with respect to x of the function log base a of x. Now, if you'll recall, we do know the derivative with respect to x of the natural log of x, right? What is it? Good, 1 over x. And then we also know that the derivative with respect to x of e to the x, this is probably one of your favorites, it's just e to the x. And then earlier we showed that the derivative with respect to x of a to the x is a to the x times ln of a. So, any guesses on what's going to happen if we need to differentiate log base a of x instead of log base e of x, the natural log? Well, let's see how it's going to work. So the process is we're going to replace log base a of x with y. We're just going to let y equal log base a of x. And then I'm going to rewrite that equation in exponential form. So this is equivalent to a to the y equals x. Okay, now I'm going to differentiate this equation with respect to x. Notice y is defined implicitly in terms of x. But have no fear, we just learned implicit differentiation, so we got this. So derivative of a to the y is going to be a to the y times ln of a, and then since I'm differentiating y with respect to x, I have to use the chain rule, multiply by dy dx. And this is equal to the derivative of x, which is just 1. Okay. So now I want to isolate dy dx, and I can do that by dividing by a to the y ln of a. So dy dx equals 1 over a to the y times natural log of a. But then remember, a to the y is equal to x. So this simplifies to 1 over x times the natural log of a. Did you guess that? So let's summarize what we have so far then. The derivative with respect to x of log base a of x is 1 over x times natural log of a. That's just a constant. If you take the derivative with respect to x of ln of x, it's just 1 over x. Really, it is 1 over x times ln of a, but since a in that case is e, right, for natural logarithm, then that's just 1 over x times 1. So you were really using this rule the whole time, you just didn't realize it. Okay, so here's kind of the thing that might help you remember the rule. When you're differentiating and the base is other than e, right, then you just multiply by ln of whatever the base is. That's if you're differentiating a to the x, or in the case of a logarithm, since the x is in the denominator, just put ln of a right next to it, okay? Good. So let's try some examples, and we're going to also include having to use the chain rule, trig functions, product rule, quotient rule, all that good stuff. So find the derivative of f of x equals the natural log of sine squared x. So to start off, f prime of x is equal to 1 over x. In this case, the entire argument is sine squared x. That goes in the denominator. So when you differentiate natural log of whatever, you put the whatever in the denominator. Then by the chain rule, I have to multiply by the derivative of sine squared x. And if it helps you to rewrite sine squared x like this, so you can see how to take the derivative more easily, go for it. So you're going to multiply by 2. Then you just have sine of x raised to the first. And then I have to apply the chain rule one more time and multiply by the derivative of sine x, which is cosine of x. All right, looking good. Let's see, can we cancel anything? Oh yeah, so this sine of x cancels with 1 factor of sine in the denominator. So now I have 2 cosine x over sine x, and this is equivalent to 2 cotangent of x. Yes, you definitely want to replace it with cotangent of x, because think about it, if you had to take, say, a second derivative and you didn't do that, then you would be stuck using the quotient rule. So always set yourself up when you're trying to decide how far to simplify. Think to yourself, can I find the zeros of this derivative easily, and am I in a good place to take another derivative? Those are often like key indicators for how simplified the derivative needs to be. You'll get a feel for it the more you practice. All right, let's try another one. Let's switch up the base since we learned how to do that now. So find the derivative of f of x equals log base 5 of x times e to the x. Okay, so f prime of x is going to equal, as soon as you see a logarithm, you just take whatever the argument is, throw it in the denominator. 1 over x e to the x, and then, oh, the base is not e, which means I need ln of that base, which is 5. Okay, nice. Now we have to use the chain rule, multiply by the derivative of x times e to the x. And when I do that, I have to use the product rule, right? Because x is one function, e to the x is the other one. So I'm going to leave x alone, multiply by the derivative of e to the x. What's that? Just e to the x. Plus, now I'm going to take the derivative of x, which is just 1, and then I leave e to the x alone. All right, let's see here. Can we clean it up? This whole expression is going to go in the numerator, and I notice I can factor out e to the x from both those terms. So let's do that. So I have e to the x times x plus 1 sitting in the numerator. And then downstairs we've got x e to the x ln of 5. Ooh, so e to the x cancels out. Very snazzy. And all I have now is x plus 1 over x times natural log of 5. And that is our final answer. Not too bad, right? Okay, let's look at a few more. Here we're finding the derivative of f of y, which equals y times natural log of 1 plus e to the y. Notice I have to use the product rule when I start because I have y, that's one function, times ln of 1 plus e to the y, that's another function. All right, so f prime of y is going to be, let's leave y alone and then take the messier derivative first. So derivative of ln of 1 plus e to the y, it's going to be 1 over, whatever's in those parentheses, 1 plus e to the y. And then I have to apply the chain rule, multiply by the derivative of 1 plus e to the y. So derivative of 1 is 0. Derivative of e to the y is e to the y. So that's the first half of the product rule. I left y alone, and then this is the derivative of natural log of 1 plus e to the y. And then I have plus, now I'm going to take the derivative of y. So that's just 1, and then I get to leave ln of 1 plus e to the y alone, right? They take turns having their derivative taken. Okay, let's see. Is this going to clean up much? So in the numerator on this first term, I'm going to have y times e to the y, okay, over 1 plus e to the y, plus, and then ln of 1 plus e to the y. That's it. That's as cleaned up as it gets. Ooh. Let's box it nicely, for goodness sake. Okay, much better. All right, you cannot distribute a natural log across addition. Ln of a plus b cannot be simplified. It does not equal ln of a plus ln of b. No, no, no. In case you're rusty on your properties of logarithms, I'll link a video here for my Precalculus playlist where I go through the logarithm properties because you're going to need it. All right, let's do another example. Here we have log base 2 of e to the negative x times cosine of pi x. Why don't you guys pause the video, give this one a try. When you do the chain rule, you're going to need to use the product rule. So see if you can do it without making any silly mistakes. Use this as a chance to test yourself, and then when you finish, hit play. All right, so here we go. So dy dx is going to equal, I have log base 2 of all of this stuff. So the stuff goes in the denominator. So I have 1 over e to the negative x cosine of pi x. And then remember, the base is not e in this problem, so I have to multiply by ln of 2. Right? If the base isn't e, you throw in ln of whatever that base is into the denominator. All right, now I have to use the chain rule, multiply by the derivative of e to the negative x cosine pi x. And it is product rule time. Okay, so let's leave e to the negative x alone. Derivative of cosine pi x. So derivative of cosine of something is negative sine something. So leave the pi x alone. And then by the chain rule, I have to multiply by the derivative of the something of pi times x, which is just pi. Plus, and then now let's go ahead and differentiate e to the negative x. So it's going to be e to the negative x, but then I have to multiply by another negative because of the chain rule. So I have negative e to the negative x, and then I leave cosine pi x alone. Ooh. All right, all right. Let's see how this is going to clean up. I'm noticing in the numerator, I can factor out an e to the negative x. So let's do that. And then I have negative pi times sine pi x plus, or actually it's going to be minus, right? Because there's a negative sitting out right here. Minus cosine pi x over e to the negative x times cosine pi x times natural log of 2. So I can cancel out this e to the negative x, hooray. And then I'm just left with negative pi sine pi x minus cosine pi x over cosine pi x times ln of 2. Let's box that with pride. That looks good. Okay. Things are looking good. As long as you just remember the rules, you should be in a good place. Okay? Consider logarithmic differentiation. Logarithmic differentiation is useful in several scenarios. One big indicator when you would want to use logarithmic differentiation is if you would just have this horrendous chain rule, quotient rule saga going on if you were to try to differentiate, as you could see we have here. Another scenario where you're going to need it, which is in the following example, but I'll just let you look at it now, is when you have a variable in the base of your function as well as in the exponent. In that case, you have to use logarithmic differentiation as well. So here's the process, and then we'll work through the examples together. First thing you do is you take the natural log of both sides of the equation. Then you're going to use your logarithmic properties to expand and simplify before you go ahead and differentiate, because the whole point is to make the equation as nice as possible to work with when you're going to differentiate it. Then you differentiate implicitly with respect to x, solve for y prime. Done. So I'll show you, it'll make more sense once we work through the steps, but just keep in mind those are like the two main scenarios. Either it looks really, really terrible, it would be a nightmare of a chain rule, or you have a variable in the base and the exponent. So here I have y equals the fourth root of x squared plus 1 over x squared minus 1. So to kick things off, we're going to take the natural log of both sides. So I have ln of y equals ln of the fourth root of x squared plus 1 over x squared minus 1. All right, now we're going to use our log properties to expand the right-hand side. So this is ln of y equals, now remember, this fourth root is the same as having this expression raised to the 1/4 power. And using our properties of logarithms, I can move that exponent to the coefficient in front on the logarithm. So I'm going to rewrite this as 1/4 natural log of x squared plus 1 over x squared minus 1. Again, I can expand further since the argument is a quotient, right? And I can rewrite this using subtraction with two logarithms. So this is 1/4 ln of x squared plus 1 minus 1/4 ln x squared minus 1. And this is all equal to natural log of y. Now, if you notice here, this is fully expanded. Hopefully you remember doing this in your pre-calc days. If not, I linked the video earlier. I'll link it again. So go back and watch it if you forgot how to expand logarithms. And we're at a good place now because if I were to differentiate, I would not have this nightmarish chain rule to apply. It would be pretty easy breezy. However, the only difference is I don't have plain old y on the left-hand side anymore, right? Since I took the natural log of both sides. It's fine though, we can do implicit differentiation. So derivative of ln of y is 1 over y times dy dx, right? And now this is equal to, okay, 1/4 just comes along for the ride. Derivative of ln of something is 1 over the something, and then by the chain rule, I have to multiply by derivative of the something, so derivative of x squared plus 1, which is just 2x. Oh, see how nice, now that all those logarithms were there separately, we didn't have to keep using complicated techniques to find the derivative. And then we have minus 1/4. Okay, now we're differentiating, so it's going to be 1 over x squared minus 1, and then derivative of x squared minus 1, 2x. Good, good, good. All right, can we clean it up a little bit? Yeah. So the 4 and the 2 are going to cancel. This is a 2. Same thing over here. So now we have 1 over y dy dx equals x over, we've got 2 times x squared plus 1 in the denominator for that first term, minus x over 2 times x squared minus 1 for the denominator in the second term. Okay, let's go ahead and get a common denominator. It's going to be 2 times x squared minus 1 times x squared plus 1. So I'll multiply this first term by x squared minus 1. And the second one by x squared plus 1. And we have 1 over y times dy dx is equal to, are you guys going to be okay? Let's just distribute and combine like terms in one shot, right? So distribute this, distribute that negative x, clean it all up. So we've got x cubed minus x cubed minus x over 2 times x squared plus 1 times x squared minus 1. Those are conjugates, so I'm going to end up with x to the 4th minus 1. All right, almost done. Notice x cubed cancels out in the numerator. All right, we've got 1 over y dy dx equals negative 2x over 2 times x to the 4th minus 1 now. And then these 2's cancel, and we're at the last step. So the last step is, remember, we want to solve for dy dx, right? I have to get it all by itself. So I'm going to multiply both sides by y, so that cancels out there. So times y. And now I have dy dx equals negative x over x to the 4th minus 1. No, you're not going to leave y in there. What do? Go back to the beginning. What was y equal to? Y was equal to the 4th root of x squared plus 1 over x squared minus 1. That's what I'm going to write for y. Times 4th root of x squared plus 1 times x squared minus 1. Okay, good. So we'll leave it like that. You could clean it up more if you wanted, because remember, x to the fourth minus 1 here. This is negative x over x squared minus 1, x squared plus 1. And then we've got in the numerator on the other term, x squared plus 1 to the 1/4 over x squared minus 1 to the 1/4. And so I can combine the exponents here. This is 1, this is 1/4. So then you have negative x squared plus 1 to the 1/4 over, and then we have x squared minus 1 to the 5/4, and then x squared plus 1. Oh my goodness, we can combine that too. It just never ends to the first. So now this will cancel, and then this is to the 3/4. Okay, I gotta rewrite it now. I mean, check with your instructor in the back of the book how far to take it. Oh, that's gone. We canceled that. That guy is gone. I mean, now it's so cleaned up, huh? X squared minus 1 to the 5/4, x squared plus 1 to the 3/4. Bam. Okay. Anyways, main idea is when you look at the original problem and it's got a lot going on, chain rule, product rule, quotient rule, all kind of nested into the same problem. Nice idea to take the natural log of both sides, expand, and then differentiate from there. Other scenario where you absolutely have to use it is when you have a variable in the base and in the exponent. X is there, X is there. You have to take the natural log of both sides. So let's do it. ln of y equals ln of cosine 5x to the x. Why do we do this? So that we can move that x to the front using our logarithm properties, all right? So we've got ln of y equals x times ln of cosine 5x. Okay, now we're going to differentiate implicitly, obviously. So derivative of ln of y is 1 over y dy dx. This part's going to be the same, right, for every problem, because you have y equals, then you do ln of y, so this will always look the same. Now on the right-hand side, we've got to use the product rule, because I have x, that's one function, times ln of cosine 5x, that's the other function. Okay, product rule time. So let's leave x alone, take the derivative of natural log of cosine 5x. So it's going to be 1 over whatever's in the parentheses, cosine 5x. Now chain rule time, take the derivative of cosine 5x. That's going to be negative sine 5x. Chain rule one more time because it wasn't plain old x, so times 5. Okay, that's only half the product rule. Plus, now let's take the derivative of x, 1. And then I leave the other function alone. He already had his turn. ln of cosine 5x. Okay, it's just cleanup time. So we've got 1 over y dy dx equals negative 5x sine 5x over cosine 5x plus ln of cosine 5x. And then just like last time, I want to multiply both sides by y, so I can find dy dx, get it all by itself. So we have here dy dx is equal to, now I'm going to write negative 5x, notice, guys, this is tangent of 5x. Yes, let's replace it, tangent of 5x plus ln of cosine 5x times y. Nope, you don't leave the y in there. You go back to the original problem and replace it. So let me copy everything back down there. Negative 5x tan 5x plus ln cosine 5x. And then what was y to begin with? Here, cosine 5x to the x. So that's what I'm going to replace it with. Cosine of 5x raised to the x. That's the final answer. Very nice. So classic problems, you'll see derivative of y equals x to the x, something like that. You have to take the natural log of both sides to proceed. All right, hope you enjoyed the video. This is a really important use of logarithms, so I hope you appreciate their beauty. Don't forget to give this a thumbs up. Subscribe if you haven't already. I would really love it. It helps support my channel, and share the video with your classmates and anyone else that you think would benefit.